Well, hello there. So let's look at some practical applications of this first order system theory that we talked about in the last lecture. We're going to solve the typical RC circuit problem using a Thevenin approach. So this is where we left off in the last lecture. We had the general response of an RC circuit. So any circuit with one capacitor and as many resistors and sources and current sources, anything like that is allowed, but just one capacitor. And so we solve for the response of this by looking at the circuit before the switch was moved. So for t less than 0, we have this one, and we assume it's in steady state. It's been there for a long time. So we have an open circuit for the capacitor. Then we move the switch to the t greater than or equal to 0, and we want the transient response of this. So we want it as a function of time. And so this one came out with a Thevenin equivalent circuit, a voltage and a resistor in series. So this represents very complicated circuits, a Thevenin plus a single capacitor. And we found the differential equation by using Kirchhoff's laws and Ohm's law and the differential equation for the capacitor. And here's the big solution. We found the voltage as a function of time for t greater than 0 was just a function of the final voltage, which is the Thevenin voltage, the initial voltage, which depends on the initial circuit, and tau, the time constant, that's our RC, the Thevenin resistance, times our one capacitor's capacitance. And that's the full solution. So just as a summary of this method, if we have any complicated circuit with one capacitor, we first will analyze the circuit in DC steady state to get the initial conditions, and we can also use this analysis for the final condition. Then for the t greater than t0 or t greater than 0 circuit, we make a Thevenin of everything, treating the capacitor as the load. So everything except the capacitor goes into the Thevenin analysis, and we make a Thevenin voltage and a Thevenin resistance for the rest of the circuit. If you do that right, the Thevenin voltage should be that final capacitor voltage that we found in this step up here. Then we have a cookbook solution from that point. It's this equation right here. We need the final voltage, we need the initial voltage, and we need the time constant, that's RC. So let's try that out on a circuit. Here's a complicated circuit. It's got a 45 volt voltage source, a 60 volt voltage source. It's got one capacitor in the middle and a switch. So the first thing is to read the problem, and it would say something like the switch was in position 1 for a long time, then at t equals 0 it was moved to position 2. Find the voltage across the capacitor as a function of time for t greater than 0. That's what we're after. We always find the voltage across the capacitor. If you need something else, you have to do a secondary calculation. So initially, the switch is here and it was there for a long time, so it's in steady state. So our initial circuit for less than 0 is on the left here, with this capacitor is replaced with an open circuit because that's the steady state condition, and we need to find the voltage here. You can see it's a voltage divider. There's no current flowing here because of the open circuit, but there is current flowing through these two resistors, so we could do the voltage divider equation and find that we have 30 volts over here. The other way to do it that the book is showing is to make a Thevenin equivalent of this circuit, and then the voltage across the capacitor is the Thevenin voltage. So once we found the initial conditions, now we move the switch to the t greater than 0 position over here at 2, and now we want to solve for the voltage as a function of time for t greater than 0. So the process is to make a Thevenin of this circuit. Once we move this switch over, this isn't connected to the capacitor anymore, so it doesn't do anything. So we just have the circuit on the right, and it looks like this. And so we want to make a Thevenin of everything except the capacitor. We're treating the capacitor as the load for the Thevenin. So terminals A and B would be here. We have to find the Thevenin of this circuit. So to find the Thevenin voltage, we remove the load, get rid of the capacitor, and we find the voltage across that capacitor. Here we have a dangling resistor. This is going to have zero current going through it for the open circuit voltage. So again, we would have a voltage divider with the 24 and 12K resistors in series. So that's the voltage divider equation. The voltage we're measuring across, the 12K divided by the sum times 60, it gives us our 20 volts, and that's our final voltage, or our Thevenin voltage. Then the second step for the Thevenin is to find the Thevenin resistance, and here we zero the source, make that a short circuit, remove the load, and try to find the equivalent resistance from here to here. So you can see we've got a 2K resistor in series with these two, which would be in parallel with a short circuit here. So 2K plus 12 in parallel with 24. Write it out on some paper if you're not sure how this came about. Thevenin's still relatively new, so practice this if you need to. But we get a 10 kilo ohm resistor for the Thevenin resistance. So here is now our Thevenin circuit, 20 volt Thevenin voltage, 10K Thevenin resistance, and our original capacitor, 20 microfarads. Now we've got it in the cookbook format, and we can just plug in the answers. So this is our equation form, our cookbook equation, V infinity plus the quantity V0 minus V infinity times e to the negative t over tau. We know that V0 was 30 volts from 2 slides ago. V infinity is the Thevenin voltage, so it's going to be 20 volts. The resistance in our time constant is the Thevenin resistance, so 10K gives us the time constant of, here's our 10K, here's where the capacitor finally comes in, 20 microfarads, 20 times 10 to the minus 6, so 0.2 seconds. Relatively slow for something like a circuit, fast maybe for a mechanical system. Talk about the time constant of the ship's rudder or something, how long it takes to reach steady state. This would be pretty fast. But if you're talking about disk drives or something like that, slow. Anyway, we've got 0.2, we've got 20, we've got 30. We put them in the right place. Here's the 1 over 0.2 gives us a 5, and the 30 minus 20 gives us the 10, and here's the 20. So this equation down to here, and we're done. All right, so I hope you feel confident in this. The steps are pretty straightforward, and they're using some of our old analyses. So if you have to brush up on Thevenin or something, go ahead. But we use that initial condition from the initial switch and steady state analysis. Then we make a Thevenin of everything except the capacitor. Then we use our cookbook and find the answer. And you're done. All right, so we'll look at this with inductors in the next video. Same process, different differential equations. See you later.